Okay, so one way we can detect is receptors literally on the surface of the cell and inside the cell. Right? So these are our pattern recognition receptors. But we also have mannose binding lectin and C-reactive protein. These are proteins we make, and their name, one of them, their name tells you what they bind to. Mannose binding lectin, right? So say a bacteria gets in. So notice this bacteria, these represent mannose. This is a sugar that's common to bacteria and I think some yeast. So we produce these proteins, mannose binding lectins. These are proteins. They'll bind to the surface of the bacteria. This helps us detect them. Why? Because look, we have two systems that recognize mannose binding lectin. We have phagocytic cells, so like macrophages and neutrophils. They have receptors for mannose binding lectin. So see how they're binding to what we actually produced, right? And what is that cell going to do? It's going to destroy it. It's literally going to engulf it, eat it, and destroy it. That's what phagocytosis does. But there's another system of proteins that we're going to talk about, the complement system. They can recognize cells coated in mannose binding lectin, and they'll produce proteins that literally will make pores in the membrane of the bacteria and directly kill that cell. That's one of the outcomes of the complement system. And this is the way, one of the ways it's activated, right, is the mannose binding lectin. Right, so it coats, right, and as I was right, yeast and bacteria. And I didn't even read this before class. C-reactive protein, which I don't have a picture for right here. Again, it's a protein we produce. It binds to phospholipids found on bacterial and fungal plasma membranes, right? And we have receptors on our phagocytic cells that recognize this. So when we use our own proteins to stick onto something and tag it as foreign, that process is called opsonization. I always think of it as tagging for destruction, because that is exactly what it does. Our antibodies, which are a product of our adaptive immune system, do the same thing, but they're very specific, right? Where this is not specific, I didn't tell you what bacteria we're binding to, right? I just said, bacteria and yeast that have mannose, we're binding to it. Bacteria and fungi that have plasma membranes that C-reactive protein can bind to, it's going to bind. What is that going to cause? Detection, right? Opsonization, which leads to destruction of those cells. Because our phagocytic cells have receptors for C-reactive protein and mannose binding lectin. So it's another way, right, we're going to detect them. Complement, a little bit more complicated. It's a series of proteins, and there's 3 ways we can activate this system. And if you think of this system as almost a domino effect, right? Once it starts, there's a cascade of events that can happen, right? To get it started, there's 3 different ways it can start. The classical pathway, the alternative pathway, or sometimes referred to as the mannose binding lectin, or just the lectin pathway. So as we saw in that first picture, right, one of the ways we can activate this system is mannose binding lectin. The classical pathway, guess what? It was called that because it was the first way we saw this got initiated, and then we learned about the alternative way. And this is one of the things that I hate. Because classical sounds like this is what happens all the time, the first thing that happens, right? An alternative is just that, the alternative? No. The alternative is probably what happens first when we see a pathogen. And the reason why is because what starts the classical is a product of our adaptive immune response. It's an antibody, right? Antibodies take time to produce if it's the very first time you've seen something. The alternative pathway, right, doesn't need prior exposure, right? And you see, remember I said before, this is a component of our innate immune system. We're born with this, right? But a component of our adaptive antibodies can activate this system. So the important thing is what starts this, right? What molecules bind to start these pathways? So this is a good animation. To play it, you have to be in presentation mode, and then you can hit play and it'll play. And I guess it's probably good that I can't get my audio to work because I'll just walk you through this one. So whole bunch of proteins, serum proteins, so they're found in your blood, right? In the liquid phase of your blood. Most of them are named C for complement and then a number. And it's actually the order in which they were discovered, not necessarily the order in which they're activated. Although we're only going to cover a small portion of this, like we're going to highlight this. So kind of like glycolysis when I talk about it in lab, right? We're not going to talk about every step, not a graduate level immunology class. I don't even have all the steps memorized anymore because I don't have to. Okay? What's important, right, is once we get this system activated, it will elicit inflammation. As you saw in that first picture, it can cause direct cell lysis, right? It can make proteins that insert into membranes and literally lyse. One of the proteins in this system when activated, opsonize. And what did I say opsonation is? What did I say that was? Tagging for destruction. So this is a molecule that's going to bind to the surface of, say, a bacterial cell and tells our system, kill that guy. Why? Because our phagocytic cells that kill have receptors for that protein. So there's a few proteins in this system that I want you to memorize. Not all of them, just a few. I'm going to help you remember them. All right, so in this video, it only shows classical and alternative. The Mannose binding lectin pathway gets started by what binding? Mannose binding lectin. That one, some of the steps are a little bit different, right? This is probably why this animation just goes over classical and alternative. So what's the first question we want to answer? What starts classical? I already told you guys the answer. What starts alternative? I didn't tell you the answer yet. Let's watch. Okay? So here we have a bacterial cell. What is first binding to the surface of that bacteria? What is first binding? An antibody, which is a product of our adaptive immune response. And then C1 represents, of course, a complement protein. Do y'all see that? So that's how classical starts. An antibody has to bind first, right? And then a cascade of events happen, right? Where molecules, complement molecules, notice there's C and then numbers, and then when they break into pieces, they're given letter designation. So when C4 is broken into two pieces, it's C4A and C4B, right? And when you really listen to this, sometimes it gets monotonous, right? And then you have enzymes. Okay, now we get the alternative pathway. And I wish they would have started out with a bacteria again. But say this is some foreign substance, right? Some foreign substance, this green thing here. They call it an endotoxin, right? Or a cell component. C3b binds to that. And I always remember B for binding, right? And then it's going to start a series of reactions that look, oh, we get C3 convertase again, which breaks C3 into C3a and C3b. both of those pathways, right, get to some point where you're taking C3 and you're splitting it. So what started the alternative pathway? C3b binds. It won't bind to our cells because we have protection against it. But we're always making it, and it will bind to bad things other than our cells. So this is basically tagging for destruction too, right? So this is the opsonin of the complement system, C3b. And again, why I always remember C3b for binding. It physically binds to the pathogen. So then we get that. So C3a actually is part of the inflammatory response, right? It's going to get the blood vessels leaky, right? Get mast cells to release things like histamine, which make the blood vessels leaky, and they're going to travel into that area. C3b, as I said, literally binds, it opsonizes to the surface of, say, a bacteria or something foreign it can bind to. Phagocytic cells have receptors for it. They're going to gobble it up and destroy it. The other thing that happens is C5 convertase forms, and C5 gets broken into its two pieces. C5a is another one important for inflammation, right? C5b starts this, the formation of that donut-shaped hole. So notice there's several proteins. I'm not going to make you memorize those. But they'll form this donut-shaped hole. This is called the MAC complex because it stands for membrane attack complex. So this is important, right? It inserts into what? Membranes. So let's step through that. So complement is actually 30 plus serum proteins that are antimicrobial. 9 of them are numbered, right? And once they start this cascade, we can get inflammation as we saw. We can get opsonization, right, which is tagging for destruction. Phagocytic cells will come eat them. Or we can directly destroy the pathogen if the MAC complex, the membrane attack complex, inserts into their membrane. So 3 separate methods of activation. The classical, which was the first discovered, right? What starts it? Antibodies. And remember, antibodies are a part of our adaptive immune response. We haven't gotten to them yet. So evolutionarily, probably much older, probably happens first is the alternative pathway, in which complement protein had to bind to start this. C3b. That's a very important complement protein. And then similar to what happens in the classical pathway, lectin binding, right, Mannose binding lectin, is another way this cascade will start. So there's a summary of it, right? We can start the alternative way with C3b binding to something like lipopolysaccharide or lipotectonic acid. Or we can get Mannose binding lectin binding to Mannose, or we can get an antibody. Antibody is classical. Mannose binding lectin is the lectin pathway. And the alternative is C3b, one of the complement proteins binding. So notice different complement proteins involved, right? But this is a common step. This conversion of C3 into its two pieces and C5a into its two pieces. So C4a, C3a, C5a, and C5b, all of these are involved in the inflammatory response. Only one of them is involved in opsonization. What is that one? C3b. All of these guys come together to form that donut-shaped hole that can cause direct lysis of the cell. What do we call that? It's Acronym is MAC, but really important that you know what it stands for. Membrane attack complex, right? So what are some of the important ones and why? So inflammation, right? Depending, because this is only involved in one of the pathways, C4A, C3A, C5A, right? These are parts of those proteins. These cause degranulation of mast cells and basophils. Mast cells and basophils, as we'll learn later, contain a pro-inflammatory cytokine that we all know very well if you experience allergy. It's called histamine, right? So they contain these little pockets, we call them granules, they're vesicles, that contain pro-inflammatory cytokines. The number one inside that cell type is histamine. C5b, that one specifically is a chemoattractant for neutrophils. It literally calls the neutrophils here, says, hey, come right here. Right? This is where the problem is. Yeah. So, here's that first picture, right? But now it's C3b that's starting it. So we know this is the alternative pathway, right, of complement activation, right? That C3 binding is called opsonization, right? Coding for destruction, right? Look at how huge I wrote that. That's how hugely important that one complement fragment protein even, right? It's part of C3. It's C3b. It can start the alternative pathway. It can opsonize, right? It's produced in all the pathways. It can tag for destruction. And it's part of starting the formation of destruction. So this shows you the classical pathway, right? This is one of those ones I think you can step through, right? All the different steps involved. So you get an idea of the reason why I show you this one. As I said, it's a series of steps that happen, right? The animation is pretty good because it's moving, right? But one thing leads to another, right? And one of the final things that can happen is this MAC complex. So it looks like this, right? Potentially. These proteins, remember, are globular, right? And this is an electron micrograph. You see all these little black holes? Those are MAC complexes. So as you imagine, this poor cell is toast, right? This is a red blood cell that was attacked by MAC complex. Why? Because it wasn't the red blood cell that was supposed to be in that person. Right? One of the ways that they get destroyed is your complement system, right, is going to attack. Usually because antibodies have recognized it. So that donut-shaped, right, structure we just looked at is the membrane attack complex. So it's most effective against gram-negative cells, less against gram-positive. See, I told you, still not shutting up about gram-positive and gram-negative. It goes all the way to the end, y'all. Okay, so these cellular differences. So if it's a membrane attack complex, anyone want to gander a guess on why gram-negatives are more susceptible to this attack? They have an outer membrane this can insert into. For gram-positives, these proteins would have to travel through what first to get to their membrane? The peptidoglycan cell wall. It can happen, just not very often, right? So this is a good attack against those gram-negatives. Do we have to leave interferon? I think we'll leave interferon for next time. So interferon, as we saw, is a viral response, right? So I highly recommend watching that video, right? We'll step through it next time, and then we're going to move on to Innate Part 4. So I don't think I'm going to turn on the next poll, but remember at the beginning of class I said I turned on, right, because we don't have enough time in class to poll. But really be testing your knowledge and be studying, right? So please, 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 please right? I even put a date on it. Before you come back to class, do this Innate Part 1, right? Because we've already covered that. You should know this stuff. I'll wait and turn on this one on Thursday. All right, I'm going to stop this recording.